Both will disappear. This is what you have to leave the bottom of vessel. Nothing to do with physics. Your grammar should be very systematic here. The sphere and the hemisphere both will simultaneously leave the bottom of the vessel. What do you mean by this? How to analyze this for in terms of physics? I'll have water. Okay, let's get into the discussion. Both will leave simultaneously. So what should happen to the rod, the light rod AB? It should remain horizontal. So what I'm going to do is first, I'll apply force. And because of that, here the tension is set up in the rod. Length of the rod is L, so let this length be X. The net torque about O should be 0. If that is 0, then both will leave simultaneously. Is it okay? What is the meaning of this? The sphere and the what is the meaning of this? I think there's a core of the problem. Huh? Means the net torque about O must be 0. Now, will you justify what I wrote? If A and B, if the rod AB remains horizontal on application of force, then only when both can leave simultaneously. If the net torque is non-zero, then suppose the net torque is clockwise. Let's assume that it's a clockwise. Then if it's a clockwise, that means A will leave, B will not lose contact. If it's anti-clockwise, B will lose contact, A will be in contact. So for both to leave simultaneously, the net torque about O must be 0. There's a fundamental idea here. For that means bottom of vessel means the net torque about O must be 0. So for that to happen, what should be the torque now? So T1 L minus X should be T2 into X. Then let's get into forces that are acting. Weight mg. The resultant force by the liquid. The resultant force by the liquid. I'll show it here. Actually, I had to show it somewhere at this particular point for convenient purpose. I'm showing it here. Similarly, here this will be T2. The liquid here will exert a force here. No? Mass of this be W1, W2 will write it. W1, W2. How this liquid will exert force normally. Now, resultant force of this, how it will be. vertically down. So shall we take this to be the resultant force should be F2. What are F1, F2? Force exerted by the liquid. And this F1, I have to show it somewhere from here. So for our convenient purpose, I'll just writing F1 there. Okay, that's like the equation T plus F1, T1 plus F1 minus W1 equals 0. What is F1? Density 2 by 3 pi r cube G minus, this will be each sphere of mass m, no? So this will be mg equal to 0. Same material and radius r. So the other sphere, the weight of this should be off of this. Or if you take this is volume V, total volume V, so this should be V by 2. In terms of that, if you are expressing, this will become rho V by 2 G, density of material, sigma Vg equals 0. Then T2 minus W2 minus F2 equals 0 on the hemisphere. So this tension T2, weight of this should be rho V by 2 sigma V by 2 G equal to rho V2 by G. Sir, what is how you write F2? Net force exerted by the liquid on the solid, what is equal to? Density of the liquid into volume immersed into G. I think I'll bring expression for T1, T2. So X is unknown thing which has to be determined. So solving this will get the required answer. Just only the idea of the forces. Huh? So here the pressure forces, you have to show it in this way. The resultant force will be vertically upward. The resultant force on both the hemisphere and solid sphere will be vertically, for a sphere will be vertically upward, for the hemisphere will be vertically downward. And how much that hydrostatic force? Directly, the density to volume immersed. A strict condition, one more. Here, so what actually happens like, practical, there's an ideal case, huh? This cannot be really so smooth that no liquid will enter. There'll be some rough and the liquid will enter here. Practically, what I mean to say is practically what happens, some liquid will rush into this, in this region, and the net for hydrostatic force will be upward. There's the ideal case we are discussing. No liquid will enter into this region. This is ideal, huh? But practically what will happen? Some liquid will come and the right hydrostatic force will be upward. This is what mistake we do. If you know buoyancy, you'll go wrong. If you don't know buoyancy, you are correct. Later on, I think next week, where if the liquid enters here, the buoyancy will come into picture. The hydrostatic force will be upward thrust will come into picture. I think you have to make a observation here afterwards. If an object is in contact with the bottom, is it rough or is it any smooth? That conditions have to be put it. I think he has explained very clearly. There's no water or air under the hemisphere. How many of you notice this? It really matters a lot. Fine. If there's a water, then the resultant force on the hemisphere should be upward, no doubt. Definitely, I can say there's a beautiful problem in fluids. Read the question.